Tonight, we're going to explore something that seems like it should have a simple answer, but actually reveals one of the most chaotic and violent stories in all of planetary science. Every planet in our solar system spins. But here's what's strange. They all formed from the same cloud of gas and dust, the same rotating disk of material swirling around the young sun. You'd think they'd all spin the same way, at roughly the same speed, tilted at roughly the same angle, but they don't. Jupiter completes a full rotation in under 10 hours. Venus takes 243 Earth days and spins backward. Uranus is tipped completely on its side, and Mercury barely rotates at all. The question is, why? And the answer involves some of the most violent events the solar system has ever seen. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something fundamental. Something so basic that you might never have stopped to think about it. Every planet spins. Right now, as you're listening to this, the ground beneath your feet is moving. Earth is rotating on its axis at about 1,040 miles per hour at the equator. You don't feel it because you were born into that motion. Everything around you, the air, the oceans, the buildings, everything is moving with you. But the rotation is real. It's why the sun appears to rise in the east and set in the west. It's why day follows night, follows day in a cycle that's been repeating for over 4.5 billion years. Now, when we talk about a planet spinning, we're really talking about three different things. First, there's the rotation speed, how quickly the planet completes one full turn. For Earth, that's about 23 hours and 56 minutes. We round it up and call it a day. Second, there's the axial tilt, the angle at which the planet's axis of rotation is leaned relative to its orbital plane around the Sun. Earth's axial tilt is about 23.4 degrees. That tilt is why we have seasons. When the northern hemisphere is tilted toward the Sun, it's summer there, and winter in the south. 6 months later, it reverses. Without that tilt, there would be no seasons at all. Every day would be roughly the same temperature at any given location year-round. Third, there's the direction of spin. Most planets in the solar system rotate counterclockwise when viewed from above their north pole. This is called prograde rotation, but not all of them do. Venus rotates clockwise. So does Uranus, sort of, because it's tilted so far that its rotation is essentially sideways. These three properties, the speed, the tilt, and the direction, together define a planet's spin state. And here's the critical point. No two planets in our solar system share the same spin state. Not even close. They're all different. Different speeds, different tilts, different orientations. The diversity is remarkable. And the question that sits at the heart of planetary science is simple. If all the planets formed from the same material, in the same system, orbiting the same star, why didn't they all end up spinning the same way? To answer that, we need to go back to the very beginning. About 4.5 billion years ago, in a relatively quiet region of the Milky Way, a vast cloud of gas and dust began to collapse. This cloud was enormous, spanning perhaps a light year or more across. It was made mostly of hydrogen and helium, the two simplest and most abundant elements in the universe, with traces of heavier elements mixed in, things like carbon, oxygen, silicon, and iron. These heavier elements had been produced inside earlier generations of stars and scattered into space when those stars exploded as supernovae. So the very material that would become our solar system was recycled stardust. Atoms forged in the hearts of dead stars billions of years before our sun even existed. Now, this cloud wasn't perfectly still. Nothing in space is ever perfectly still. There were slight motions within it, tiny currents and flows caused by the gravitational influence of nearby stars, by pressure waves from distant supernovae, by magnetic fields threading through the interstellar medium. These motions were small, almost negligible, but they were there. And critically, these motions had a net rotation, not a fast rotation, not a dramatic spin, just a very slight overall tendency to rotate in one direction. When part of this cloud began to collapse under its own gravity, something important happened. The cloud got smaller. As it shrank, it began to spin faster. This isn't something unique to space. It's a fundamental law of physics called the conservation of angular momentum. Angular momentum is essentially a measure of how much rotational motion an object has. It depends on the mass of the object, how fast it's spinning, and how far that mass is distributed from the axis of rotation. The key property of angular momentum is that in an isolated system, it's conserved. It doesn't go away. It can't be created or destroyed. It can only be transferred from one thing to another. You've probably seen this principle in action, even if you didn't know the name. Think of a figure skater doing a spin on the ice. When the skater pulls their arms in close to their body, they spin faster. When they extend their arms, they slow down. Their angular momentum stays the same throughout. When the arms are extended, the mass is spread farther from the axis of rotation, so the rotation speed has to be slower to keep angular momentum constant. When the arms come in, the mass is concentrated closer to the axis, and the rotation speed increases to compensate. Same angular momentum, different configuration. This is exactly what happened with the collapsing cloud. As the cloud shrank from perhaps a light year across down to the size of our solar system, its slight initial rotation got amplified enormously. The material that was drifting almost imperceptibly in one direction before the collapse was now spinning much, much faster. And as it spun faster, the cloud flattened. This is also a consequence of physics. The collapsing material wanted to fall straight toward the center, pulled by gravity, but the rotation pushed material outward at the equator through centrifugal force. The result was a compromise. Material falling toward the center along the axis of rotation could fall freely, but material at the equator was partially supported by its rotational motion. So the cloud flattened into a disk, a thin rotating disk of gas and dust surrounding a hot, dense core at the center. That core would become the sun, and the disk, that flat rotating structure extending outward from the young sun, is what we call the protoplanetary disk. This disk is where every planet, every moon, every asteroid, and every comet in our solar system would eventually form. And here's the thing that matters most for understanding planetary spin. The disk was rotating. The entire disk was going around in one direction, counterclockwise when viewed from above the sun's north pole. Everything in the disk was orbiting the sun in the same direction, following the same overall flow. This is why most planets today orbit the sun in the same direction and roughly in the same plane. They inherited that motion from the disk they formed in. And you might think that since everything in the disk was rotating the same way, all the planets should have ended up spinning the same way too. Same direction, same speed, same tilt. But that's not what happened. And to understand why, we need to look at how planets actually formed out of this disk. The disk wasn't a smooth, uniform sheet of material. It had structure, denser regions and thinner regions. Variations in temperature from the blisteringly hot inner regions near the young sun to the frigid outer regions far from it. In the inner disk, close to the sun, temperatures were high enough that only rock and metal could exist as solid particles. Lighter substances like water, ammonia, and methane were in gaseous form because the heat kept them vaporized. Farther out, beyond a boundary called the frost line or snow line, temperatures dropped low enough for these volatiles to condense into solid ice crystals. This matters because beyond the frost line, there was simply more solid material available to build things. Both rock and ice, instead of just rock. This distinction would later help explain why the outer planets grew so much larger than the inner ones. But for now, what matters is that solid particles existed throughout the disk. Tiny grains of dust and ice, each no larger than specks of sand, drifting through the rotating gas. These grains began to stick together. When two tiny particles collided gently enough, they could adhere to each other through electrostatic forces and surface interactions. Over time, these tiny particles grew into larger clumps. Clumps grew into pebbles. Pebbles grew into rocks. Rocks grew into boulders. This process, called accretion, was slow at first but accelerated as objects got bigger. The larger an object became, the stronger its gravitational pull, and the more effectively it could attract additional material. Eventually, these growing objects reached sizes of about 1 kilometer across. At this stage, we call them planetesimals. Planetesimals were the building blocks of the planets. There were billions of them in the disk, each orbiting the sun, each with its own slightly different velocity and trajectory. They were all going around in roughly the same direction because they inherited the disk's overall rotation, but not exactly the same direction. Each planetesimal had its own small deviations, tiny differences in speed, and orbital inclination caused by gravitational interactions with other planetesimals, by pressure effects in the gas disk, by random variations in how the material was distributed. These differences were small, but they were crucial. As planetesimals collided and merged, building up larger and larger bodies called protoplanets, each collision imparted angular momentum to the growing body. When a planetesimal hit a protoplanet, it didn't just add mass, it added rotational motion. The direction and amount of spin that each impact contributed depended on the angle at which the planetesimal struck, the speed of the impact, and where on the protoplanet's surface the collision occurred. Imagine a protoplanet sitting in space, and a planetesimal comes in and strikes it slightly off-center. That off-center impact delivers a torque, a rotational push. If the planetesimal hits on the left side, it tends to spin the protoplanet one way. If it hits on the right, it tends to spin it the other way. Now, because all the planetesimals were generally orbiting in the same direction as the disk, there was a statistical bias. On average, more impacts would come in from the prograde direction, tending to give the protoplanet a prograde spin, a rotation in the same direction as its orbit around the sun. This is why most planets ended up with prograde rotation. The disk's overall motion biased the impacts in that direction. But here's the key insight, and it's the thing that explains why the planets don't all spin identically. While the average of all those impacts favored prograde rotation, each individual impact was different. Some came in at steep angles, some came in nearly head-on, some were fast, some were slow. Some hit near the equator, some hit near the poles. Each impact added its own unique contribution to the growing planet's spin. And because no two planets experienced the exact same sequence of collisions, no two planets ended up with the exact same spin. Think of it this way. Imagine you're building a planet by throwing billions of balls of clay at it from all directions. Most of the balls are coming from roughly the same side because of the disk's rotation, so the planet tends to spin one way, but each ball hits at a slightly different spot, a slightly different angle, a slightly different speed. The final spin of the planet depends on the cumulative effect of every single impact. And since no two planets experience the same pattern of impacts, no two planets end up spinning the same way. This process is inherently chaotic. In physics, when we say something is chaotic, we mean that tiny differences in initial conditions can lead to vastly different outcomes. The exact sequence of collisions that built each planet was different. The sizes of the impacting bodies were different. The timing was different. The geometry was different. All of these factors combined to produce a unique spin state for each planet. Even if you could rewind the clock and start the solar system over with almost exactly the same initial conditions, the planets would likely end up with different spins the second time around. The outcome is sensitive to the precise details of every collision, and those details are effectively random. This is a profound point and worth spending a moment on. Many people assume that the solar system formed in an orderly, deterministic way, that the laws of physics determined exactly where each planet would be, how big it would be, and how fast it would spin. But that's not how it works. The laws of physics set the rules of the game. Conservation of angular momentum, gravitational attraction, the dynamics of collision and accretion, these are the rules. But within those rules, there's enormous room for variation. The specific outcome depends on the exact details of a process that involves billions of individual events, each of which is slightly different. The result is a solar system that's governed by predictable physics, but shaped by unpredictable history. Let me give you a sense of just how different the planet's spins are, because the numbers really drive this home. Earth rotates once every 23 hours and 56 minutes. Mars is surprisingly similar at 24 hours and 37 minutes. But that similarity is a coincidence, not a consequence of any shared mechanism. Jupiter, the largest planet, rotates in just 9 hours and 56 minutes. That's less than 10 hours for a planet that's over 11 times wider than Earth. The equator of Jupiter moves at about 28,000 miles per hour. Saturn isn't far behind at 10 hours and 33 minutes. These gas giants are spinning incredibly fast. On the other end of the spectrum, Venus takes 243 Earth days to complete one rotation, and it rotates backward in the opposite direction from its orbit around the Sun. Mercury rotates once every 58.6 Earth days. These are extraordinarily slow compared to Earth or Jupiter. And Uranus is tilted about 98 degrees from vertical, essentially rolling along its orbit on its side. Each of these wildly different spin states emerged from the same disk of material, the same starting conditions, broadly speaking. But the specific chaotic history of each planet's formation produced a completely different outcome. Now, I want to be precise about something because it's important for understanding what comes later. The spin that each planet acquired during accretion was not its final spin. Accretion gave each planet an initial rotation state, but that initial state was then modified, sometimes dramatically by events that happen later. Giant impacts could change a planet's spin in an instant. tidal interactions could alter it gradually over billions of years. Atmospheric effects could play a role for planets with thick atmospheres. The spin you see today is not necessarily the spin the planet had when it first formed. It's the result of everything that happened afterward. But the accretion process set the stage. It established the baseline. It determined the general tendency for prograde rotation and the rough range of spin speeds. And it introduced the fundamental randomness that ensured no two planets would be the same. Let me talk about the disk itself for a moment, because its properties also influenced how planets acquired their spin. The protoplanetary disk wasn't static. It evolved over time. The gas in the disk was slowly dissipating, either falling onto the young sun, being blown away by the sun's radiation and stellar winds, or being incorporated into the forming planets. This dissipation happened over a period of roughly 3 to 10 million years. That might sound like a long time, but by astronomical standards it's remarkably brief. The solar system had only a few million years to build its planets before the raw material was gone. The timing of planet formation relative to the disk's lifetime mattered for spin. Planets that formed quickly, while the disk was still dense and gas-rich, experienced different conditions than planets that formed later when the disk was thinning out. The gas in the disk could exert drag on growing protoplanets, affecting their orbits and potentially influencing their rotation. In regions where the gas was dense, this drag could be significant. In regions where the gas was thin, it was negligible. Since different planets formed at different distances from the Sun and at different times during the disk's evolution, they each experienced different levels of gas interaction. This added yet another layer of variation to the spin each planet acquired. There's also the question of where in the disk each planet formed. The inner disk, close to the Sun, was a crowded, violent place. Planetesimals were packed more densely here. Collisions were more frequent and often more energetic because orbital speeds are higher closer to the Sun. The outer disk was more spread out. Orbital speeds were slower. Collisions were less frequent. These differences in environment meant that the accretion process played out differently for each planet. An inner planet like Earth was built from frequent, high-speed collisions in a crowded region. An outer planet like Jupiter began as a rocky, icy core in a less crowded region, but with access to vastly more material because of the ice beyond the frost line. The size the planetesimals involved in building each planet also mattered. If a planet was built primarily from many small impacts, the spin contributions would tend to average out more smoothly. Each small impact adds a tiny nudge, and when you add up billions of tiny nudges, the random variations tend to cancel each other out to some degree. The result is a spin state that reflects the overall statistical bias of the disk, prograde, moderate speed. But if a planet experienced one or more very large impacts during its formation, those single events could dominate. A single large impact can deliver more angular momentum than thousands of smaller ones combined. It can spin a planet up, spin it down, tilt its axis, or even reverse its rotation entirely. The larger the impactor relative to the target, the more dramatic the effect. And this is where the story of the planetary spin takes its most dramatic turn. During the final stages of planet formation, the solar system was not a peaceful place. It was a demolition derby. Protoplanets the size of Mars or larger were careening through the inner solar system, their orbits destabilized by gravitational interactions with each other. These massive bodies collided in events of almost inconceivable violence, impacts that released more energy than all the nuclear weapons ever built, multiplied by millions. These collisions could shatter worlds, melt entire planets, strip away atmospheres, and fundamentally reshape whatever they struck. These giant impacts didn't just add mass, they completely reset the rotational states of the planets they struck. A single collision between two Mars-sized bodies could take a slowly spinning world and turn it into a rapidly spinning one, or vice versa. It could take a planet spinning prograde and flip it to retrograde. It could tilt an axis from 0 degrees to 90 degrees in a matter of hours. This is why the initial spin from accretion, while important as a starting point, was often overwritten. For the rocky planets in particular, the final spin state was likely determined not by the cumulative effect of billions of small impacts, but by the last few giant impacts they experienced. The last big collision essentially erased the memory of everything that came before and set a new spin state from scratch. We know this happened because we can see the evidence. Earth has a large moon that almost certainly formed from such a collision. Uranus is tilted 98 degrees, which is very difficult to explain without at least one enormous impact. Venus rotates backward, which is extremely difficult to produce through accretion alone. Mercury's slow rotation, while partly explained by tidal forces from the Sun, may also have been influenced by a massive ancient impact that stripped away much of its outer layers. The evidence is all around us. The fingerprints of giant impacts are written into the spin states of nearly every rocky planet. But we need to be careful here. It would be tempting to say that giant impacts explain everything, that every unusual spin state is the result of some ancient collision, but that's an oversimplification. Giant impacts were certainly important, probably dominant for the rocky planets, but they weren't the only factor. The initial spin from accretion mattered. The gravitational interactions between planets mattered. Tidal forces from the Sun mattered. The internal structure and evolution of each planet mattered. The explanation for why every planet spins differently is not a single mechanism. It's a combination of many mechanisms, each contributing in different ways for different planets. And that's what makes this story so fascinating. There's no single answer to the question of why the planets spin differently. The answer is that planetary spin emerges from a complex interplay of physics and chance. The laws of conservation of angular momentum determine the general rules, but the specific outcome for each planet depends on its unique history, a history shaped by where it formed, what it was made of, how it grew, what hit it, and how the gravitational environment around it evolved over billions of years. The protoplanetary disk gave every planet a starting point. It gave them all a tendency toward prograde rotation and provided the raw angular momentum that would be distributed among the forming worlds. But from that common starting point, each planet followed its own path. Each one accumulated mass in a slightly different way, experienced a different pattern of impacts, and ended up with a unique spin state as a result. This is the first piece of the puzzle, the birth of spin, angular momentum from the collapsing cloud, concentrated and distributed through the protoplanetary disk, delivered to each planet through the chaotic process of accretion. It explains why most planets spin prograde. It explains why there's variation. And it sets the stage for the dramatic events that would reshape those spins into the wildly diverse rotation states we observe today. Because what happened next, in the final violent stages of planet formation, would prove even more consequential than the accretion process itself. So the protoplanetary disk gave every planet a starting spin. Angular momentum from the collapsing cloud was distributed through the disk, delivered to each growing world through billions of small collisions, and biased toward prograde rotation by the overall flow of material. If the story ended there, the planets would all spin in roughly the same direction at roughly comparable speeds. There would be variation, certainly, because accretion is messy and statistical, but the variation would be modest. You'd expect all 8 planets to rotate prograde at speeds within a reasonable range of each other. Maybe some would spin in 15 hours, others in 30. There might be slight differences in axial tilt, a few degrees here or there, but nothing dramatic. Nothing like what we actually see. What we actually see is chaos. Venus rotates backward, Uranus lies on its side, Mercury barely rotates at all. Earth's axis is tilted at 23.4 degrees, giving us our seasons. Mars is tilted at a similar angle, about 25 degrees, but its tilt wobbles chaotically over millions of years, in a way Earth's doesn't. The spin states of the planets are wildly diverse, far more diverse than the accretion process alone could produce. Something else happened. Something violent. Something that took the relatively modest variations produced by accretion and amplified them into the dramatic differences we observe today. That something was giant impacts. And to understand what giant impacts did to planetary spin, you need to understand just how violent the final stages of planet formation really were. The early solar system was not the orderly place it is today. Today, the planets orbit the sun in nearly circular paths, well separated from each other, stable and predictable. But 4.5 billion years ago, the inner solar system was a war zone. Dozens of protoplanets, some as large as Mars or even larger, were orbiting the young sun in paths that crossed and overlapped. Their orbits were not stable. Gravitational interactions between these protoplanets constantly perturbed their trajectories, pulling them into new orbits, nudging them closer together, setting them on collision courses. And the chaos wasn't limited to the inner solar system. The giant planets themselves played a major role in stirring things up. In the early solar system, Jupiter and Saturn were not in the orbits they occupy today. They formed closer together and then migrated, shifting their orbits apart over millions of years as they interacted gravitationally with the remaining disk of gas and with the swarms of planetesimals surrounding them. This migration had enormous consequences for the rest of the solar system. As Jupiter and Saturn shifted their orbits, their gravitational influence swept through regions of space that had previously been stable. Gravitational resonances, specific orbital ratios where the periodic pull of a giant planet amplifies rather than cancels out over time, move through the solar system like waves. Objects that had been orbiting peacefully for millions of years suddenly found their orbits destabilized. This process, studied extensively through computer simulations beginning in the early 2000s, shows that the migration of Jupiter and Saturn likely triggered a period of intense instability across the entire solar system. The orbits of Uranus and Neptune were disrupted, the Kuiper belt was scattered, and critically for our story, the inner solar system was flooded with debris. Asteroids and protoplanets that had been in stable or nearly stable orbits were flung onto new trajectories, many of them crossing the paths of the forming terrestrial planets. This gravitational upheaval dramatically increased both the frequency and the energy of collisions in the inner solar system. It didn't just make impacts more likely, It made them more violent because the destabilized objects were arriving on more eccentric, higher energy orbits. They were hitting harder and from more varied directions than they would have in a calmer system. This is important for understanding planetary spin, because it means the giant impact era wasn't just an inevitable consequence of having many protoplanets in a small space. It was amplified and intensified by the gravitational influence of the outer giants. Jupiter and Saturn, from their distant orbits, were stirring the pot. They were the hidden drivers of much of the violence that reshaped the rocky planets. The very worlds whose spins were set by orderly gas accretion and gravitational contraction were simultaneously scrambling the spins of the smaller worlds closer to the Sun. The gas giants shaped their own rotation through smooth, predictable physics. And then they helped ensure that the rocky planet's rotations would be shaped by chaos and violence instead. Computer simulations of planet formation consistently show that this phase of the solar system's history was extraordinarily violent. The final assembly of the terrestrial planets, the process that took us from dozens of Mars-sized protoplanets to 4 finished rocky planets, happened through a series of catastrophic collisions. These weren't gentle mergers. They were impacts at speeds of several miles per second, releasing energy on a scale that's almost impossible to comprehend. When 2 Mars-sized bodies collide at those speeds, the energy released is roughly equivalent to billions of nuclear weapons detonating simultaneously. The impact melts both bodies completely. Rock is vaporized. Iron cores are liquefied and splashed across space. The collision creates a cloud of superheated debris that can take thousands or even millions of years to cool and reassemble. These giant impacts didn't just build the planets, they fundamentally reshaped them. And one of the most important things they reshaped was planetary spin. Because when a body the size of Mars slams into a body the size of Earth, the angular momentum delivered by that single collision can completely overwhelm whatever spin the target planet had before. One impact can spin a planet up, slow it down, tilt its axis by tens of degrees, or even reverse its rotation entirely. The pre-existing spin from accretion becomes almost irrelevant. The last giant impact effectively resets the clock, establishing a new spin state that has little or no memory of what came before. The most dramatic and well-studied example of a giant impact in our solar system is the one that created Earth's moon. The leading theory for the moon's origin, called the giant impact hypothesis, proposes that about 4.5 billion years ago, a Mars-sized body struck the young Earth. This impactor, sometimes called Theia after the Greek goddess who was the mother of the moon goddess Selene, hit Earth at an oblique angle at a speed of roughly several miles per second. The collision was catastrophic. Both bodies were largely melted or vaporized. Theia's iron core sank into Earth's interior and merged with Earth's own core. The outer rocky layers of both bodies were blasted into space, creating an enormous cloud of superheated debris that spread out into a disk around the battered Earth. Over time, this debris disk cooled, and the material within it began to accrete, clumping together under its own gravity. Within perhaps a few thousand years, this debris had coalesced into a new body, the Moon. Our moon is unusually large relative to its planet. Its diameter is about 27% of Earth's diameter. No other planet-moon pair in the inner solar system has such a large ratio. This alone is a clue that the moon didn't form through some gentle process. It formed in violence, born from the debris of a world-shattering collision. But here's what matters for our story. The Theia impact didn't just create the moon, it dramatically altered Earth's spin. Before the impact, Earth had whatever rotation it had accumulated through accretion, probably a prograde spin of perhaps 10 to 20 hours per rotation. The impact changed everything. The oblique angle of the collision delivered an enormous amount of angular momentum. Simulations of the impact suggest that immediately after the collision, the Earth-Moon system was rotating extremely rapidly. Earth may have been spinning with a day as short as 5 to 6 hours. The axis of rotation was also affected. The impact likely tilted Earth's axis significantly, though the exact tilt immediately after the collision is debated. The 23.4 degree tilt we have today has been modified over billions of years by gravitational interactions with the Moon, the Sun, and the other planets. The important point is this. If you asked what determines Earth's spin, the answer isn't primarily the billions of small accretion events that built the planet over millions of years. The answer is predominantly one single event. One collision. One moment of extreme violence that delivered more angular momentum in a matter of hours than all the previous accretion events combined. Earth's spin today is fundamentally a product of the Theia impact, modified by billions of years of tidal interaction with the Moon and Sun. The accretion history set the initial conditions, but the giant impact overwrote them. Now, Earth isn't the only planet that bears the scars of giant impacts. Let's look at Uranus, because Uranus might be the most striking example of how a single collision can transform a planet's entire rotational identity. Uranus is tilted 98 degrees from vertical. This is extreme. Most planets have axial tilts that range from near zero, like Mercury at about 0.03 degrees, to moderate values like Earth's 23.4 degrees or Mars's 25 degrees. Even Saturn, with a tilt of about 26.7 degrees, and Neptune at about 28.3 degrees, have tilts that fall within a range that can be explained by the normal messiness of accretion and modest perturbations. But 98 degrees is far outside that range. Uranus isn't just tilted. It's lying on its side. Its axis of rotation is nearly in the plane of its orbit. During its 84-year journey around the Sun, Uranus's north pole sometimes points almost directly at the Sun, giving that hemisphere decades of continuous sunlight, while the opposite hemisphere sits in decades of continuous darkness. This extreme tilt is very difficult to explain without invoking a giant impact. Computer simulations have shown that a single collision with an Earth-sized body, or perhaps 1 to 3 times the mass of Earth, striking Uranus at the right angle and speed, could have tipped it over. The impactor would have had to hit at a specific oblique angle, delivering angular momentum perpendicular to Uranus's original spin axis. The result would be a planet whose axis was rotated by nearly 90 degrees, while its rotation speed remained relatively fast. Uranus currently rotates in about 17 hours and 14 minutes, which is reasonably fast for a planet its size. The impact didn't stop it from spinning, it just changed the direction in which it spins. Some researchers have proposed that instead of one giant impact, Uranus might have been tipped by 2 or more smaller but still very large collisions. Multiple impacts, each delivering a significant angular momentum kick, could have cumulatively tilted the axis to its current extreme value. This scenario has some advantages. It might better explain certain features of the Uranian system, like the orbits and compositions of its moons and rings, which orbit in the plane of Uranus's tilted equator rather than in the plane of its orbit around the Sun. If the moons and rings form from debris generated by the impact or impacts, they would naturally end up in the equatorial plane of the tilted planet. However, one major impact versus multiple smaller ones remains an open question. Both scenarios can produce the observed tilt. Both are physically plausible. And the evidence we have, while strongly supporting the general idea of impact-driven tilting, isn't detailed enough to distinguish definitively between the two scenarios. What we can say with confidence is that some kind of giant collision or collisions happened to Uranus early in the solar system's history, and that collision fundamentally transformed its rotational state from something relatively normal into the bizarre sideways spin we see today. The case of Uranus also illustrates something important about the timing of these events. The impact that tipped Uranus almost certainly happened during or shortly after the period of giant planet formation, probably within the first few 100 million years of the solar system's history. This is when the solar system was most chaotic, when large bodies were most likely to be on crossing orbits, when the gravitational interactions between forming planets were strongest. As the solar system settled into its current more stable configuration, the likelihood of giant impacts decreased dramatically. The planets found their orbits. The remaining debris was either swept up or ejected from the solar system. The violence subsided. Whatever spin state each planet had at the end of this chaotic period was essentially locked in, at least as far as giant impacts were concerned. Later modifications would come from tidal forces and other slow processes, but the era of spin resetting collisions was over. Now let's consider Venus, because Venus is another world whose spin almost certainly bears the imprint of extreme events. Venus rotates retrograde. It spins clockwise when viewed from above its north pole, the opposite direction from most other planets. And it rotates extremely slowly. One full rotation takes 243 Earth days. That's actually longer than Venus's year, which is about 225 Earth days. So on Venus, a day is longer than a year. If you could stand on the surface of Venus, which you couldn't because the temperature is about 900 degrees Fahrenheit, and the atmospheric pressure is roughly 90 times that of Earth. But if you could, the sun would rise in the west and set in the east. And it would take about 117 Earth days from one sunrise to the next because of the combination of Venus's slow retrograde rotation and its orbital motion around the sun. How did Venus end up spinning backward? One possibility is a giant impact. Just as a massive collision could have tipped Uranus onto its side, a sufficiently large impact could have reversed Venus's rotation or slowed it down so dramatically that tidal forces from the sun eventually took over and drove it into retrograde rotation. There are computer simulations showing that a single large impact, perhaps a body 1/2 to 1 times the mass of Earth hitting Venus at the right angle, could have reversed its spin direction or nearly stopped its rotation entirely. But Venus's retrograde rotation is complicated because there are other mechanisms that might explain it without requiring a catastrophic impact. The sun's gravitational tidal forces have been acting on Venus for 4.5 billion years. Venus orbits relatively close to the sun, only about 67 million miles away. At that distance, solar tidal forces are significant. These forces tend to slow a planet's rotation over time. Given enough time, solar tides could have dramatically slowed Venus's rotation from whatever faster rate it started with. But tidal forces alone would typically slow a planet to a tidally locked state, where one face always points at the Sun, or into some spin-orbit resonance like Mercury's 3-2 lock. They wouldn't normally produce retrograde rotation. Something extra is needed. And that something might be Venus's extraordinarily thick atmosphere. But that's a story about long-term tidal evolution, which we'll explore more deeply later. For now, the key point about Venus is that its retrograde spin could be the result of a giant impact, or it could be the result of a complex interplay between impact history and billions of years of tidal and atmospheric effects, or some combination of both. The truth is, we don't know for certain which mechanism is primarily responsible. Venus guards its secrets closely. Let's also consider Mars, because while Mars doesn't have as dramatic a spin story as Uranus or Venus, it still shows signs of a violent past. Mars currently has an axial tilt of about 25.2 degrees, similar to Earth's, and it rotates in about 24 hours and 37 minutes, also similar to Earth. These similarities might seem to suggest that Mars and Earth had similar formation histories, but the similarities are probably coincidental. Mars is much smaller than Earth, only about half its diameter and roughly 10% of its mass. Its formation involved different numbers and sizes of impactors in a different region of the protoplanetary disk. What's interesting about Mars is that its axial tilt is not stable. Unlike Earth, whose tilt is stabilized by the gravitational influence of our large moon, Mars doesn't have a large stabilizing moon. Phobos and Deimos are tiny, captured asteroids with almost no gravitational influence on Mars's axial dynamics. Without a large moon to anchor its tilt, Mars's axis wobbles chaotically over millions of years. Computer simulations by astronomers Jacques Lascar and Philippe Robutel in the 1990s showed that Mars's axial tilt has probably varied between about 10 degrees and 60 degrees over the past several billion years. It might have even reached higher values at some points in its history. These wild swings in tilt are not caused by impacts. They're caused by gravitational resonances between Mars's axial precession and the orbital motions of other planets, primarily Jupiter. When these motions fall into resonance, they can pump Mars's tilt to extreme values over timescales of millions of years. Earth avoids this fate because the moon's gravitational influence keeps Earth's precession rate fast enough to avoid these dangerous resonances. This is one of the ways the moon has been crucial for Earth's long-term stability. Mars also has the Borealis Basin, one of the largest impact structures in the entire solar system. This enormous basin covers most of Mars's northern hemisphere, creating a dramatic difference in elevation between the low, flat northern lowlands and the high, cratered southern highlands. The basin is roughly 5,300 miles across and represents the scar of an ancient impact by a body perhaps 1,000 to 2,000 miles in diameter. This impact, which probably occurred in the first few 100 million years of Mars's history, would have delivered a tremendous amount of angular momentum to Mars. It may have significantly altered Mars's rotation rate and axial tilt at the time. Whatever spin Mars had before this collision would have been substantially changed by it. Mercury presents yet another case worth examining through the lens of giant impacts. Though Mercury's current spin state has been so thoroughly modified by solar tidal forces that the original impact history is harder to reconstruct. Mercury is a strange planet in many ways. It's the smallest planet in the solar system, only about 3,032 miles in diameter, but it's extremely dense for its size. Mercury has a huge iron core that makes up roughly 85% of its radius. By comparison, Earth's iron core makes up only about 55% of its radius. Mercury's core is proportionally enormous. One leading explanation for Mercury's oversized core is that Mercury was once much larger, perhaps comparable to Mars in size, and that a giant impact stripped away much of its rocky outer layers. This is sometimes called the giant impact stripping hypothesis. In this scenario, a large body struck the young Mercury with enough energy to blast away a substantial fraction of its silicate mantle and crust, leaving behind a planet that was mostly iron core with only a thin veneer of rock on top. If this happened, the impact would have also dramatically affected Mercury's rotation. A collision violent enough to strip away half a planet's mass would deliver an enormous amount of angular momentum, potentially spinning Mercury up, slowing it down, or changing its axial tilt significantly. However, Mercury's current rotation is almost entirely determined by solar tidal forces, rather than by its original post-impact spin. Mercury orbits so close to the Sun that tidal braking has been the dominant influence on its rotation for most of its history. Whatever spin Mercury had after the hypothesized stripping impact has been long since erased by billions of years of tidal interaction with the Sun. Mercury's current 58.6-day rotation period and its 3-to-2 spin-orbit resonance are products of tidal physics, not of the original impact. But the impact may have influenced the planet's internal structure in ways that affected how tidal forces operated. So even here, the connection between ancient impacts and present-day spin is not entirely severed. Now, I want to step back and make a broader point about what giant impacts mean for the diversity of planetary spin. The key insight is this: giant impacts are stochastic events. Stochastic means random, or at least effectively random from the perspective of predicting outcomes. You cannot predict when a giant impact will happen, how large the impactor will be, what angle it will strike at, or what speed it will be traveling. These are all determined by the complex gravitational dynamics of dozens of protoplanets orbiting in a chaotic system where tiny differences in initial conditions lead to vastly different outcomes. Because giant impacts are stochastic, the spin states they produce are also stochastic. Two solar systems that start with almost identical initial conditions, the same mass of material, the same general distribution, the same overall angular momentum, would end up with completely different planetary spins, because the specific sequence of giant impacts in each system would be different. In one system, the third planet might get hit by a Mars-sized body at a 45-degree angle and end up with a 23-degree tilt and a 24-hour day. In another system, the third planet might get hit from a different direction and end up tilted 60 degrees with a 12-hour day. In a third system, the third planet might avoid any late giant impacts entirely and end up with a 5-degree tilt and a 15-hour day. This is a profoundly important realization. The spin states of the planets are not determined by the laws of physics alone. They're determined by the laws of physics combined with a specific historical sequence of events that could easily have been different. The laws of physics set the rules, the constraints, the range of possible outcomes. But within those constraints, the specific outcome depends on the specific history. And that history is, for all practical purposes, random. This means that if you could somehow rewind the solar system to its initial state and let it evolve again, the planets would almost certainly end up with different spins. Earth might have a 15-degree tilt instead of 23.4 degrees. Uranus might be tilted at 40 degrees instead of 98. Venus might rotate prograde instead of retrograde. The specific spin states we observe are contingent facts about our particular solar system. They are not universal truths that would be replicated in every solar system that forms. This also means that when we look at exoplanetary systems of planets orbiting other stars, we should expect enormous diversity in planetary spin states. Every exoplanet experienced its own unique sequence of collisions during formation. Everyone had its own particular giant impact history. The diversity of spins in our solar system, from Jupiter's 10-hour prograde rotation to Venus's 243-day retrograde crawl, is just a small sample of the diversity that must exist across the galaxy. Some exoplanets probably spin even faster than Jupiter. Others probably rotate retrograde like Venus. Some might have axial tilts even more extreme than Uranus's 98 degrees. The possibilities are almost limitless because the giant impact history of each planet is unique and unrepeatable. There's one more thing I want to emphasize about giant impacts before we move on, because it's a subtle point that's easy to miss. Giant impacts don't just change a planet's spin in isolation. They change a planet's spin in the context of everything else that's happening to the planet at the same time. A giant impact can melt the planet's entire surface, destroying any early crust and creating a global magma ocean. It can strip away the planet's atmosphere, removing whatever gases had accumulated up to that point. It can change the planet's internal structure, mixing materials from the impactor's core with the target planet's core. It can create moons from the ejected debris, and those moons then exert their own gravitational influence on the planet's spin going forward. The Theia impact that created Earth's moon is a perfect example. The impact didn't just set Earth's rotation rate, it also created the moon. And the moon, through tidal interactions, has been modifying Earth's rotation ever since. The moon has slowed Earth's spin from a roughly 5 to 6 hour day immediately after the impact to our current 24-hour day. It has stabilized Earth's axial tilt, preventing the kind of chaotic wobbling that Mars experiences. It has created the tides that have shaped Earth's coastlines, influenced the evolution of life, and played a role in the development of Earth's climate system. A single collision event, lasting perhaps a few hours, set in motion a chain of consequences that have been unfolding for 4.5 billion years and continue to unfold today. Similarly, the impact that tipped Uranus affected not just the planet's spin, but its entire satellite system. Uranus's moons orbit in the plane of the planet's tilted equator, not in the plane of its orbit around the Sun. This strongly suggests that the moons formed after the tilting impact, either from debris generated by the collision or from a disk of material that reformed around the tilted planet. The impact didn't just change how Uranus spins, it determined the entire architecture of the Uranian system. These cascading consequences show that giant impacts are not isolated events. They're transformative events. They reshape everything about a planet, from its interior to its surface, to its atmosphere, to its satellite system, to its spin. And because each planet experienced a different set of these transformative events, each planet ended up being a fundamentally different world. This is why the planets in our solar system are so diverse, not just in their spins, but in everything. Their sizes, their compositions, their atmospheres, their magnetic fields, their moon systems, All of these properties reflect the unique history of each planet. And giant impacts are a major reason why those histories diverge so dramatically from what might have been a relatively uniform starting point. The accretion process built the planets from a common pool of material following common physical laws, but the giant impacts that occurred during the final stages of assembly injected randomness and chaos into the system. They took planets that might have been broadly similar and made them dramatically different. They are the reason Earth has a large moon and seasons and a 24-hour day. They are the reason Uranus lies on its side. They may be the reason Venus rotates backward. They are a major part of the reason Mercury has such an enormous iron core relative to its size. And they remind us that the solar system we live in is not the only possible solar system that could have formed from the same raw materials. It's one specific outcome of a process that has deep elements of chance built into it. The planets could have turned out differently. Earth could have been tilted differently, rotating at a different speed, orbiting at a slightly different distance. The solar system we inhabit, the one that allowed life to develop on this particular planet with this particular axial tilt and this particular day length, is the product of specific events that didn't have to happen the way they did. Giant impacts set the stage for the modern solar system. They are the bridge between the orderly physics of disk accretion and the chaotic diversity of the worlds we see today. They explain why the planets don't all spin the same way even though they formed from the same material. And they explain why the differences are so dramatic. Not subtle variations around a common theme, but wildly different spin states. Each one the unique signature of a specific, violent, unrepeatable history. But the story of planetary spin doesn't end with the last giant impact. The collisions eventually stopped. The solar system settled down. The planets found their orbits, and the remaining debris was cleared away. Yet even after the violence ended, the spins of the planets continued to evolve, slowly, gently, but persistently, because gravity never stops working. And over billions of years, the quiet, persistent pull of gravity can be just as transformative as a single catastrophic collision. The mechanisms that have been reshaping planetary spin ever since the impact stopped are different in character. They're gradual rather than sudden, patient rather than violent, but their cumulative effects have been just as profound for certain worlds in our solar system. Now let's turn our attention to something that might seem puzzling at first. If you line up all 8 planets by how fast they rotate, a pattern jumps out almost immediately. The gas giants, Jupiter and Saturn, spin far faster than any of the rocky planets. And when I say far faster, I mean dramatically, almost absurdly faster. Jupiter, the largest planet in the solar system, completes a full rotation in just 9 hours and 56 minutes. Think about that. This is a planet with a diameter of about 86,881 miles. It's over 11 times wider than Earth. If you laid Earth side by side, you'd need more than 11 of them just to span Jupiter's equator. And yet this enormous world spins around once in less than 10 hours. That's less than half the time it takes Earth to rotate, even though Jupiter is incomparably larger. Saturn is nearly as fast. It completes a rotation in about 10 hours and 33 minutes. Saturn is roughly 9.5 times wider than Earth, yet it spins more than twice as quickly. The equator of Jupiter moves at about 28,000 miles per hour. Saturn's equator moves at about 22,000 miles per hour. For comparison, Earth's equator moves at about 1,040 miles per hour. The gas giants are spinning at speeds that, when you really think about them, are almost difficult to believe for objects that massive. Now compare that to the rocky planets. Mercury rotates once every 58.6 Earth days. Venus takes 243 Earth days. Earth takes about 24 hours. Mars takes about 24 hours and 37 minutes. The rocky planets rotate relatively slowly. Some of them extremely slowly. The gas giants rotate extremely fast. This isn't a coincidence. There's a deep physical reason for it, and understanding that reason requires us to look at how the gas giants formed. Because their formation process was fundamentally different from how the rocky planets came together. In the inner solar system, the rocky planets formed through the accumulation of solid material. Dust grains stuck together to form pebbles. Pebbles merged into boulders. Boulders combined into planetesimals. Planetesimals collided to build protoplanets. And eventually, after millions of years of increasingly violent collisions, the 4 rocky planets emerged. This was a process built on solid material, rock, and metal coming together through physical contact. Every piece of mass had to literally hit the growing planet and stick. The angular momentum delivered to each rocky planet came from the sum of all those individual impacts, each one arriving at a different angle, a different speed, a different location on the surface. The gas giants formed differently. They start the same way, with a rocky and icy core that grew through accretion of solid material, just like the rocky planets. But here's where the paths diverge. Beyond the frost line, roughly around where Jupiter orbits today, the protoplanetary disk contained much more solid material than the inner disk. Water ice, ammonia ice, methane ice, all of these substances existed as solid particles out there because the temperatures were low enough. This meant there was much more raw material available to build planetary cores. And because there was more material, the cores could grow larger. When a core reached a critical mass, estimated to be somewhere around 10 to 15 times the mass of Earth, something dramatic happened. The core's gravity became strong enough to begin pulling in not just solid material, but the surrounding hydrogen and helium gas from the protoplanetary disk. And unlike solid accretion, which happens one collision at a time, gas accretion can happen rapidly. Once a core crosses that critical mass threshold, gas begins to flow onto it in a process that accelerates as the planet grows. The more gas it captures, the stronger its gravity becomes. The stronger its gravity, the more gas it can capture. This runaway process can add enormous amounts of mass in a relatively short time. Jupiter, for instance, accumulated hundreds of Earth masses worth of hydrogen and helium gas in perhaps just a few million years. That's an extraordinary amount of material gathered in an astronomically brief period. Now, here's where the spin story gets interesting. That gas didn't just fall straight down onto the core. It couldn't. The gas was orbiting the Sun as part of the protoplanetary disk. It had angular momentum. As it fell towards the growing planet's gravity well, it spiraled inward rather than plunging directly in. Think of water going down a drain. Water doesn't fall straight through the drain. It spirals because it has sideways motion. The same principle applies to gas falling onto a forming planet. The gas spirals inward, forming a smaller disk around the planet itself called a circumplanetary disk. As the gas from this circumplanetary disk eventually settled onto the planet, it brought its angular momentum with it. Each parcel of gas that joined the planet added not just mass, but rotational energy. And because the gas was spiraling in from a disk that was rotating in the same direction as the overall protoplanetary disk, the angular momentum it delivered was consistently prograde. Unlike the rocky planets, where individual impacts could come in from various angles and partially cancel each other's rotational contributions, gas accretion delivered angular momentum in a much more coherent, organized fashion. The gas was flowing in from a rotating disk, so its angular momentum was systematically biased in one direction. But the gas accretion alone doesn't fully explain why the gas giants spin so fast. The key mechanism is something more fundamental. It's the same principle we discussed earlier with the collapsing molecular cloud, and it's the same principle you see in the figure skater pulling in their arms. Conservation of angular momentum. When Jupiter was still forming, it was much larger than it is today. Not in mass necessarily, but in physical size. The young Jupiter was a hot, bloated ball of gas, puffed up by the heat generated during its formation. As the planet formed, enormous amounts of gravitational energy were released. When gas falls toward a massive object, it accelerates. When it hits the planet or slams into other infalling gas, that kinetic energy is converted into heat. The young Jupiter was extremely hot, with internal temperatures far higher than it has today. And because hot gas expands, the young Jupiter was significantly larger in diameter than the Jupiter we see now. Over millions and then billions of years, Jupiter slowly radiated this heat away into space. As it cooled, it contracted. It shrank. Not by a trivial amount. Jupiter today is still radiating about 1.7 times as much energy as it receives from the Sun. It's still cooling and contracting even now, 4.5 billion years after it formed. But the bulk of the contraction happened in the first few 100 million years. And here is the crucial point. As Jupiter contracted, as its mass pulled itself into a smaller and smaller volume, its rotation sped up. Conservation of angular momentum demanded it. The angular momentum the planet possessed when it was large and bloated had to be conserved. When the mass moved closer to the axis of rotation, the rotation rate had to increase to keep the total angular momentum the same. It's exactly the ice skater effect. Arms out, slow spin. Arms in, fast spin. Except instead of arms, it was an entire planet contracting under its own gravity. And instead of a modest increase in spin speed, the effect was enormous because the contraction was enormous. This is why Jupiter spins so fast today. It isn't because Jupiter was hit by some massive impactor that spun it up. It isn't because the accretion process happened to deliver an unusually large amount of angular momentum. It's because Jupiter accumulated a tremendous amount of gas. That gas carried significant angular momentum from the circumplanetary disk, and then the entire planet contracted from a larger initial size to its current size, spinning faster and faster as it shrank. The rapid rotation of Jupiter is a natural, almost inevitable consequence of how gas giant planets form. Saturn experienced the same process. It too accumulated a massive envelope of hydrogen and helium gas around a rocky and icy core. It too was initially larger and hotter than it is today. It too contracted over time, spinning up as it shrank. Saturn's slightly slower rotation compared to Jupiter, 10 hours and 33 minutes versus 9 hours and 56 minutes, reflects differences in its formation history. Saturn is less massive than Jupiter, about 95 Earth masses compared to Jupiter's 318 Earth masses. It likely accumulated its gas more slowly, and may have started with a somewhat different angular momentum budget, but the basic mechanism is the same. Gas accretion followed by gravitational contraction spun both worlds up to their rapid rotation rates. Let me emphasize how different this is from what happened to the rocky planets. The rocky planets acquired their spin almost entirely through the cumulative effect of solid body impacts. Each impact was a discrete event. Each one contributed angular momentum in a somewhat random direction. The final spin state was the messy statistical result of millions or billions of individual collisions, plus a few dominant giant impacts that could override everything else. The gas giants, by contrast, acquired much of their spin through a fundamentally smoother process. Gas flowing in from a circumplanetary disk, delivering angular momentum in a coherent, organized direction. Then gravitational contraction amplifying that spin. The process was less chaotic, more systematic, and it naturally produced fast rotation rates. This also explains something else that might not be obvious at first. The gas giants are not only spinning fast, they're spinning in the prograde direction counterclockwise when viewed from above the North Pole, consistent with the original rotation of the protoplanetary disk. This makes perfect sense if their spin was acquired primarily through gas accretion from a disk that was itself rotating prograde. There was no giant impact to knock them over or reverse their rotation because, well, what would hit them? By the time the gas giants had finished forming, they were so massive that nothing in the solar system could deliver the kind of impact needed to significantly alter their spin. Jupiter contains more mass than all the other planets combined. To substantially change Jupiter's rotation, you'd need an impactor comparable in mass to several Earths hitting at just the right angle with just the right speed. Nothing that large existed in the solar system by the time Jupiter had finished growing. This is a key distinction between the gas giants and the rocky planets. The rocky planets were vulnerable to having their spins dramatically altered by giant impacts because they were relatively small. A Mars-sized body hitting the young Earth could fundamentally change Earth's rotation, because the impactor was a significant fraction of Earth's own mass. But a Mars-sized body hitting Jupiter would be like throwing a pebble at a bowling ball. It would add a tiny amount of angular momentum, but it wouldn't change the overall spin in any meaningful way. Jupiter's spin was set during formation and has remained essentially unchanged ever since. The same is true for Saturn. Now, let's talk about the internal structure of the gas giants, because their composition plays an important role in how they rotate. Unlike the rocky planets, which are solid bodies with well-defined surfaces, the gas giants are fluid. They're made almost entirely of hydrogen and helium in various states. At the cloud tops, the hydrogen and helium exist as gas. Deeper down, as pressure increases, the hydrogen gradually transitions into a liquid state. There's no sharp boundary, no ocean surface. The gas just gets denser and denser until it behaves more like a liquid. Even deeper still, at pressures millions of times greater than Earth's atmospheric pressure, hydrogen is squeezed so tightly that it enters an exotic state called metallic hydrogen. In this state, hydrogen atoms are packed so closely that their electrons are stripped free and can move between atoms, just like electrons in a metal. This metallic hydrogen layer is electrically conductive and is thought to generate Jupiter's powerful magnetic field, the strongest planetary magnetic field in the solar system. At the very center of Jupiter, there may be a rocky and icy core. This core, the original seed around which the gas giant grew, is estimated to contain perhaps 10 to 15 Earth masses of rock and ice. Though recent data from NASA's Juno spacecraft suggests the core may not be a compact solid ball. Instead, it might be a dilute core, a region where heavy elements are mixed in with the surrounding hydrogen rather than concentrated in a distinct solid sphere. This is still an active area of research, and scientists are debating what Juno's measurements really tell us about Jupiter's deep interior. The fact that Jupiter and Saturn are fluid has important consequences for their rotation. Solid bodies like Earth rotate as a unit. Every part of the planet, from the core to the surface, completes one rotation in the same amount of time. But fluid bodies don't have to work that way. Different parts can rotate at different speeds. This is called differential rotation, and we observe it directly on both Jupiter and Saturn. On Jupiter, the equatorial region rotates slightly faster than the polar regions. The difference isn't huge, about 5 minutes over a full rotation period, but it's real and measurable. We can see it because different cloud bands at different latitudes move at slightly different speeds. The equatorial zone completes a rotation in about 9 hours and 50 minutes. The higher latitudes take about 9 hours and 55 minutes. This differential rotation is driven by the same forces that create Jupiter's distinctive banded appearance. The planet's rapid rotation, combined with convective motions in its atmosphere where heat from the interior rises while cooler material sinks, creates alternating bands of east-flowing and west-flowing winds. These wind patterns are incredibly stable. They've been observed for centuries and show no signs of changing. Saturn shows even more dramatic differential rotation. Its equatorial region rotates significantly faster than its poles. The winds at Saturn's equator blow at speeds of up to 1,100 miles per hour relative to the deeper interior. This is an astonishing speed. These winds create a very pronounced bulge at Saturn's equator. Saturn is actually the most oblate planet in the solar system, meaning it's the most flattened at the poles and widest at the equator. Saturn's equatorial diameter is about 7,300 miles larger than its polar diameter. If you look at a good photograph of Saturn, you can actually see that it's slightly squashed. It's not quite a perfect sphere. It's noticeably wider than it is tall. This oblateness is a direct consequence of its rapid rotation combined with its fluid composition. The fast spin flings material outward at the equator, just as the original protoplanetary disk was flattened by the rotation of the collapsing molecular cloud. Differential rotation makes it surprisingly tricky to even define what we mean by a gas giant's rotation period. For a rocky planet like Earth, it's straightforward. The whole planet rotates together, so you just measure how long one full rotation takes. But for Jupiter or Saturn, the cloud tops at different latitudes rotate at different speeds. Which speed do you use? Astronomers solve this problem by measuring the rotation of the planet's magnetic field rather than its cloud tops. The magnetic field is generated deep inside the planet, in the metallic hydrogen layer, and it rotates with the bulk interior rather than the differentially rotating atmosphere. Jupiter's magnetic field rotates once every 9 hours and 55 minutes and 30 seconds. That's considered Jupiter's true rotation period, the rotation of its deep interior. Saturn's internal rotation period was harder to pin down because its magnetic field is almost perfectly aligned with its rotation axis, which makes it difficult to use magnetic field measurements to determine the rotation rate. It took data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, to nail down Saturn's internal rotation period at about 10 hours and 33 minutes. Now let's shift to Uranus and Neptune, because these two planets offer a fascinating contrast to Jupiter and Saturn. Uranus and Neptune are often called ice giants rather than gas giants, and this distinction is important. While Jupiter and Saturn are composed primarily of hydrogen and helium, Uranus and Neptune have a very different composition. They have relatively thin hydrogen and helium atmospheres compared to their overall size. Below those atmospheres, most of their mass is thought to consist of heavier substances, water, ammonia, and methane in compressed fluid or icy states. Their rocky and icy cores make up a much larger fraction of their total mass compared to Jupiter and Saturn. Why does this matter for spin? Because Uranus and Neptune didn't undergo the same dramatic runaway gas accretion that Jupiter and Saturn experienced. They formed farther from the Sun, in a region where the protoplanetary disk was less dense and where orbital timescales were longer. By the time their cores grew large enough to start capturing significant amounts of gas, the protoplanetary disk may have already been dissipating. The gas was being blown away by the young sun's increasing radiation and stellar winds. So Uranus and Neptune captured much less gas than Jupiter and Saturn did. They ended up smaller and less dominated by hydrogen and helium. This different formation history gave them different spin characteristics. Uranus rotates once every 17 hours and 14 minutes. Neptune rotates once every 16 hours and 6 minutes. These are faster than any of the rocky planets, but significantly slower than Jupiter or Saturn. This makes sense in the context of their formation. They accumulated less gas overall, so they received less angular momentum from gas accretion, and they underwent less dramatic gravitational contraction because they're smaller and less dominated by lightweight hydrogen that could puff up dramatically and then shrink. But here's where Uranus becomes truly strange. Its axial tilt is about 98 degrees. This means Uranus is essentially tipped over on its side. Its north pole sometimes points almost directly at the Sun. During Uranus's 84-year orbit, each pole gets about 42 years of continuous sunlight, followed by 42 years of continuous darkness. This extreme tilt cannot be explained by gas accretion or gravitational contraction or any gradual process. Something violent had to happen to Uranus to tip it over. And as we discussed earlier, the leading explanation is one or more giant impacts during the late stages of planet formation. This is where the stories of the gas giants and the rocky planets converge. Even though the gas giants acquired their spin primarily through gas accretion and contraction rather than through discrete impacts, they weren't completely immune to the violence of the early solar system. Uranus, being smaller and less massive than Jupiter or Saturn, was more vulnerable to having its spin altered by a large impact. A body perhaps 1 to 3 times the mass of Earth, hitting Uranus at the right angle, could have tipped it over while leaving its rotation speed relatively fast. The impact didn't stop Uranus from spinning. It changed the direction of the spin, tilting the axis by nearly 90 degrees, while the planet continued to rotate at roughly the same speed. Neptune's axial tilt of about 28 degrees is much more modest than Uranus's, but it's still significant. It's close to Earth's tilt of 23.4 degrees. This moderate tilt could have been produced by smaller impacts during formation, by gravitational interactions with other planets during the early solar system's period of orbital migration, or by a combination of both. Neptune's tilt doesn't require any single catastrophic event to explain. It falls within the range of what you'd expect from the normal messiness of planet formation. The ice giants also show differential rotation, though in a different pattern than Jupiter and Saturn. On Uranus and Neptune, the equatorial regions actually rotate more slowly than the mid-latitudes. This is the opposite of what we see on Jupiter, where the equator spins fastest. The atmospheric dynamics on Uranus and Neptune are driven by different processes because these planets have different internal heat distributions. Neptune radiates about 2.6 times as much energy as it receives from the Sun, indicating a substantial internal heat source. Uranus, by contrast, radiates very little excess heat. This difference in internal heating likely explains the differences in their atmospheric circulation patterns and therefore their differential rotation profiles. The wind speeds on Neptune are extraordinary. Despite being the farthest planet from the Sun and receiving very little solar energy, Neptune has the fastest winds in the solar system. Wind speeds near the equator reach up to 1,200 miles per hour. These extreme winds are powered primarily by Neptune's internal heat, rather than by solar energy. Uranus, with its much weaker internal heat source, has comparatively weaker winds, though they can still reach several hundred miles per hour. So when we look at the four giant planets together, a clear picture emerges. All four acquired significant angular momentum through gas accretion from the protoplanetary disk. All four experienced gravitational contraction that amplified their rotation rates through conservation of angular momentum. But the details differed because their formation histories differed. Jupiter and Saturn captured enormous envelopes of hydrogen and helium, experienced dramatic contraction, and ended up spinning very fast. Uranus and Neptune captured less gas, experienced less contraction, and ended up spinning at intermediate rates, faster than the rocky planets but slower than the gas giants. And the specific quirks of each planet's spin, like Uranus's extreme tilt or Saturn's extraordinary ablateness, reflect the unique details of each planet's individual history. There's one more thing worth mentioning here because it connects the spin of the gas giants to a broader principle in planetary science. The rapid rotation of Jupiter and Saturn has real physical consequences. It shapes their weather, creating the distinctive banded patterns of alternating wind zones. It generates their oblateness, making them wider at the equator than at the poles. It influences the structure and dynamics of their ring systems and the orbits of their moons. Rotation isn't just a number. It's an active force that shapes every aspect of a planet's behavior. Jupiter's rapid spin, combined with its metallic hydrogen interior and internal heat, generates the most powerful magnetic field of any planet in the solar system. Jupiter's magnetosphere extends millions of miles into space, far larger than the Sun itself in some dimensions. This magnetic field traps charged particles, creating intense radiation belts that are dangerous even to spacecraft. The Juno spacecraft, which has been orbiting Jupiter since 2016, was designed with heavy radiation shielding specifically because of these belts. The connection between rotation and magnetic field generation is direct. A faster spinning conducting fluid generates a stronger dynamo effect, producing a stronger magnetic field. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and its rapid rotation is a major reason why. Saturn's rapid rotation similarly powers its magnetic field, though Saturn's field is much weaker than Jupiter's. Interestingly, Saturn's magnetic field strength at its cloud tops is actually comparable to Earth's surface field, even though Saturn is vastly larger. This is partly because Saturn's metallic hydrogen layer is thought to be smaller relative to its overall size, and partly because of differences in the structure and depth of its interior dynamo. The gas giants show us that planetary spin is not just a consequence of formation history. It's an active driver of planetary evolution. The speed at which a planet rotates influences its shape, its weather, its magnetic field, its ability to retain an atmosphere, and even the stability of its ring systems and moon orbits. Spin is not a passive property. It's an integral part of what makes each planet the world it is. And the remarkable thing is that these incredibly fast rotations, these 10-hour days on worlds vast enough to swallow hundreds of Earths, are not the result of any dramatic singular event. They're the natural outcome of physics. Gas flowed inward. Angular momentum was delivered. Gravity contracted the planet. Rotation accelerated. The laws of physics made this inevitable. The fast spins of Jupiter and Saturn are not anomalies. They're predictions. If you understand how gas giant planets form, you would predict that they should rotate quickly. And they do. This stands in stark contrast to the rocky planets, whose spins were shaped more by randomness and violence. The gas giants remind us that while planetary spin can be chaotic and unpredictable, it can also be the straightforward result of well-understood physical principles applied to the specific conditions of giant planet formation. The universe, it turns out, can be both chaotic and orderly at the same time. It depends on which part you're looking at and what forces are at play. But even the gas giants don't exist in isolation. They orbit a star. Their moons orbit them. And over billions of years, these gravitational relationships continue to shape and reshape the rotational states of worlds throughout the solar system. Some of those changes are subtle, operating over timescales so long that they're almost invisible from a human perspective. Others are dramatic enough that they have completely transformed how certain worlds move through space. And understanding those long-term gravitational effects is essential to completing the picture of why every planet spins differently. So far, we've traced the story of planetary spin from its origins in the collapsing molecular cloud, through the chaotic violence of giant impacts, and into the physics of gas giant formation and contraction. But there's one more piece of this story, and in many ways it's the most remarkable of all. Because even after the planets finish forming, even after the last giant impacts are settled, and the protoplanetary disk had dissipated into nothing, the spins of the planets were still not final. They were still changing. Slowly. Almost imperceptibly, but relentlessly. Gravity doesn't stop working just because a planet has finished forming. And over billions of years, the patient, persistent pull of gravity has continued to reshape how worlds rotate. This process is called tidal interaction, and it has done more to alter the spin states of certain planets than anything else in the history of the solar system. To understand tidal interactions, you need to first understand what a tide actually is. Most people associate tides with the ocean. Twice a day, and the ocean rises and falls along the shore. High tide comes in, low tide goes out, and the cycle repeats. This happens because of the moon's gravity, but here's what most people don't realize. Tides aren't just about water. Tides are a gravitational phenomenon that affects everything. Rock, metal, gas, ice, everything responds to tidal forces. Tidal forces exist whenever one body orbits another because gravity isn't uniform. It gets stronger the closer you are to the source. Let me explain what that means in practice. The moon orbits Earth an average distance of about 238,855 miles. Earth's gravity pulls on the moon, keeping it in orbit. But the moon's gravity also pulls on Earth. And here's the key. The side of Earth facing the moon is about 8,000 miles closer to the moon than the side facing away. That 8,000 miles, which is just Earth's diameter, means the moon's gravitational pull is slightly stronger on the near side of Earth than on the far side. This difference in gravitational pull across the diameter of a body is what creates a tidal force. The near side gets pulled toward the moon more strongly than the center, and the center gets pulled more strongly than the far side. The result is a stretching effect. Earth gets slightly elongated along the line connecting it to the moon. It's pulled into a very subtle oval shape, slightly longer in the direction of the moon and slightly shorter perpendicular to it. This stretching is tiny. For the solid body of the Earth, the tidal bulge in the rock is only about a foot in height. You'd never notice it standing on the surface, but the oceans, being fluid, respond much more dramatically. The water on the near side of Earth bulges toward the moon, and the water on the far side bulges away from the moon. This creates two high tides on opposite sides of the planet, which is why most coastal locations experience roughly 2 high tides per day, as Earth rotates beneath these tidal bulges. Now, here's where this connects to planetary spin. Earth rotates faster than the moon orbits. Earth completes one rotation in about 24 hours, but the moon takes about 27.3 days to complete one orbit. This means Earth's rotation is constantly carrying the tidal bulge ahead of the moon. The bulge doesn't point exactly at the moon, it's pulled slightly ahead by Earth's rotation. And because the tidal bulge has mass, it exerts a gravitational pull on the moon. This pull is asymmetric because the bulge is slightly ahead of the moon. The near side bulge, which is closer to the moon and therefore exerts a stronger pull, tugs the moon forward in its orbit. This gives the moon a tiny bit of extra orbital energy, which causes it to slowly spiral outward. But there's a cost. The energy to push the moon outward has to come from somewhere, and it comes from Earth's rotation. The tidal interaction transfers angular momentum from Earth's spin to the moon's orbit. Earth's rotation is gradually slowing down. The days are getting longer. Not by much. Only about 2.3 milliseconds per century. You'd never notice in a single lifetime. But over billions of years, this adds up to an enormous change. When the Earth-Moon system first formed, about 4.5 billion years ago, Earth was rotating much faster. A day on the early Earth was probably only about 6 to 8 hours long. The moon was much closer, perhaps only about 15,000 miles away, compared to its current distance of nearly 239,000 miles. Over billions of years, tidal interactions have gradually slowed Earth's rotation and pushed the moon farther away. The moon is still receding at a rate of about 1.5 inches per year, and Earth days are still getting longer. And this isn't just theoretical. The evidence that Earth's rotation has been slowing is literally written in stone. Fossil corals from the Devonian period, roughly 380 million years ago, provide some of the most compelling proof. Corals grow in daily layers, thin bands of material deposited with each day-night cycle, similar to tree rings but on a much finer scale. By counting these growth bands within annual cycles marked by seasonal changes in the coral structure, paleontologists have determined how many days there were in a year during the Devonian. The answer is about 400. Not 365. 400. Since the length of a year hasn't changed significantly, because Earth's orbital period around the Sun is essentially stable, those extra days mean each individual day was shorter. A Devonian day lasted only about 22 hours. The Earth was spinning faster, and tidal friction from the moon had not yet slowed it to its present rate. Even older evidence comes from structures called tidal rhythmites. These are layered sedimentary deposits found in ancient tidal flats and shallow marine environments. Each layer records a single tidal cycle, the rise and fall of ancient oceans. By analyzing the spacing and thickness of these layers, geologists can reconstruct the tidal patterns of the distant past, including the number of tidal cycles per month and per year. Tidal rhythmites from Australia, dating to about 620 million years ago, suggest that a day at that time lasted only about 21.9 hours. Going even further back, rhythmites from about 2.4 billion years ago indicate days of roughly 17 hours. The record is clear and consistent. The further back you go in Earth's history, the shorter the days were. Earth has been steadily decelerating for billions of years, its rotational energy being siphoned away by the moon's gravitational pull, one tide at a time. This physical evidence transforms the abstract physics of angular momentum transfer into something you can touch and measure. The proof of Earth's changing spin is embedded in ancient rock, preserved in the growth patterns of organisms that lived hundreds of millions of years ago. The tidal slowing of Earth's rotation isn't a prediction waiting to be confirmed. It's a fact documented by the geological record across billions of years. This same process has had an even more dramatic effect on the moon itself. The moon is tidally locked to Earth. That means the moon's rotation period is exactly equal to its orbital period. The moon takes about 27.3 days to orbit Earth, and it also takes exactly 27.3 days to rotate once on its axis. This is why we always see the same face of the moon. The near side always faces Earth. The far side, sometimes incorrectly called the dark side, always faces away. The far side isn't actually dark. It gets just as much sunlight as the near side. We just never see it from Earth because the moon's rotation is perfectly synchronized with its orbit. This synchronization didn't happen by accident. It happened because of tidal forces. Just as the moon raises tides on Earth, Earth raises tides on the moon. And because Earth is much more massive than the moon, the tidal forces Earth exerts on the moon are much stronger than the forces the moon exerts on Earth. In the early history of the Earth-Moon system, the moon was rotating faster than it orbited. Earth's tidal forces created a bulge on the moon that was carried ahead of the Earth-Moon line by the moon's rotation. This bulge exerted a torque on the moon, slowing its rotation. Over millions of years, the moon's rotation gradually decelerated until it matched its orbital period. At that point, the tidal bulge pointed directly at Earth, the torque vanished, and the system reached equilibrium. The moon was tidally locked. Tidal locking is not unique to our moon. It's extremely common in the solar system. Almost every large moon that orbits close to its planet is tidally locked. The 4 Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, are all tidally locked to Jupiter. They always show the same face to their parent planet. Titan, Saturn's largest moon, is tidally locked to Saturn. Triton, Neptune's largest moon, is tidally locked to Neptune. Charon, Pluto's largest moon, is tidally locked to Pluto. And in a remarkable twist, Pluto itself is tidally locked to Charon. The two bodies always show the same faces to each other, a state called mutual tidal locking. If you stood on the Charon-facing side of Pluto, Charon would hang motionless in your sky, never rising or setting, never moving at all. And if you stood on the Pluto-facing side of Charon, Pluto would do the same. The two worlds are locked in a perpetual gravitational embrace, each one's rotation perfectly matched to their shared orbital dance. Tidal locking is the end state of tidal evolution. Given enough time, tidal forces will always try to synchronize a body's rotation with its orbit. The only question is how long it takes. For small moons close to massive planets, it happens quickly, perhaps within a few million years. For larger bodies orbiting farther from their partners, it takes longer, much longer. And for some systems, the age of the solar system hasn't been long enough for tidal locking to be achieved. This brings us to Mercury, because Mercury is one of the most fascinating examples of how tidal forces shape planetary spin. Mercury orbits very close to the Sun. Its average distance is only about 36 million miles, less than 40% of Earth's distance. At this close proximity, the Sun's tidal forces on Mercury are extremely strong, much stronger than the Moon's tidal forces on Earth. Over billions of years, these tidal forces have dramatically slowed Mercury's rotation. When Mercury first formed, it was almost certainly spinning much faster, probably rotating in just a few hours like the other planets after accretion. But the Sun's relentless tidal pull has been breaking Mercury's rotation for 4.5 billion years. You might expect that Mercury would be tidally locked to the Sun, just as the Moon is locked to Earth. For a long time, astronomers assumed exactly that. They thought Mercury always showed the same face to the Sun, with one hemisphere in permanent scorching daylight and the other in permanent freezing darkness. But in 1965, radar observations from the Arecibo Observatory in Puerto Rico revealed something unexpected. Mercury wasn't tidally locked. It was rotating, slowly, but it was definitely rotating. Its rotation period turned out to be 58.6 Earth days, while its orbital period around the Sun is 87.9 Earth days. At first, this seemed puzzling. Why would tidal forces slow Mercury down but not lock it? The answer lies in Mercury's orbit, which is highly elliptical. Mercury's distance from the Sun varies significantly over the course of its orbit. At its closest approach, called perihelion, Mercury is about 29 million miles from the Sun. At its farthest point, called aphelion, it's about 43 million miles away. This variation matters because tidal forces depend strongly on distance. They decrease with the cube of the distance, so when Mercury is at perihelion, the Sun's tidal pull is much, much stronger than when it's at aphelion. Instead of locking into a 1-to-1 resonance, where one rotation equals one orbit, Mercury locked into a 3-to-2 resonance. Mercury rotates exactly 3 times for every 2 orbits around the Sun. This means that Mercury's rotation period of 58.6 days is exactly 2/3 of its orbital period of 87.9 days. This 3-to-2 ratio isn't approximate. It's precise. It's a stable gravitational resonance, maintained by the interaction between Mercury's elliptical orbit and the Sun's tidal forces. If Mercury's rotation were to speed up or slow down slightly, the tidal forces would push it back into the 3-to-2 resonance. The planet is locked, just not in the 1-to-1 ratio we see with the Moon. This 3-to-2 resonance creates a bizarre day-night cycle on Mercury. A solar day on Mercury, measured from one sunrise to the next, lasts about 176 Earth days. That's exactly 2 Mercury years. If you stood on Mercury's surface, you'd watch the sun rise, then cross the sky unimaginably slowly over the course of about 88 Earth days, set, and then stay below the horizon for another 88 Earth days before rising again. During the long day, surface temperatures reach about 800 degrees Fahrenheit. During the long night, they plummet to about minus 290 degrees Fahrenheit. This extreme temperature swing over 1,000 degrees between day and night is a direct consequence of Mercury's tidally modified spin. Mercury's story illustrates a critical point. Tidal forces don't just stop rotation. They can lock a planet into a specific resonance that depends on the details of its orbit. The one-to-one lock that we see with the Moon is the most common outcome, but it's not the only possible outcome. Mercury's elliptical orbit allowed it to settle into a 3-to-2 resonance instead. If Mercury's orbit were more circular, it probably would have ended up in a 1-to-1 lock. The specific resonance a body falls into depends on the eccentricity of its orbit, the strength of the tidal forces, and the internal structure of the body. Now let's talk about Venus, because Venus presents perhaps the most mysterious spin story in the entire solar system. Venus rotates once every 243 Earth days. That's longer than its year, which is only about 225 Earth days, and it rotates retrograde, backward compared to its orbit and compared to the rotation direction of most other planets. Venus's retrograde rotation has puzzled scientists for decades, and there's still no single universally accepted explanation for it. One possibility is that Venus was knocked into retrograde rotation by a giant impact early in its history. Just as we believe happened to Uranus, a sufficiently large impactor hitting at the right angle could have reversed Venus's spin or tipped it upside down, which would have the same effect. Venus's axial tilt is about 177 degrees. That's almost exactly 180 degrees, meaning Venus is essentially upside down compared to most other planets. If you think of Venus as being flipped, then its rotation is actually prograde with respect to its own inverted poles. It's retrograde only because we define rotation direction relative to the planet's orbit, and Venus's axis is nearly fully inverted. But here's where things get complicated. There's another explanation that doesn't require a giant impact at all. The Sun's tidal forces, combined with the tidal effects of Venus's extremely thick atmosphere, may have gradually brought Venus to its current state. Venus has the densest atmosphere of any rocky planet. The surface pressure is about 90 times Earth's atmospheric pressure. That's equivalent to the pressure you'd experience roughly 3,000 feet underwater in Earth's oceans. This massive atmosphere isn't just sitting there passively. It responds to solar heating, and it interacts gravitationally with the solid body of the planet beneath it. Solar thermal tides are created when the Sun heats Venus's atmosphere unevenly. The side of Venus facing the Sun is heated more than the night side. This creates a thermal bulge in the atmosphere on the Sun-facing side. This atmospheric bulge has mass, and it interacts gravitationally with both the Sun and the solid body of Venus beneath it. The result is a torque on Venus that works against the solid body tidal torque from the Sun. The solid body tide tries to slow Venus's rotation and lock it into a resonance with the Sun, just like what happened to Mercury. But the atmospheric thermal tide pushes in the opposite direction under certain conditions. The competition between these two torques can produce a stable equilibrium, where Venus rotates very slowly in the retrograde direction. Recent computer simulations have shown that this mechanism can naturally produce Venus's current spin state, starting from a variety of initial conditions. Whether Venus originally had a fast prograde rotation, a slow prograde rotation, or even was briefly locked in a different state, the combined effects of solid body solar tides and atmospheric thermal tides could have driven it to its current slow retrograde rotation over billions of years. This would mean Venus's strange spin isn't the result of a violent impact at all. It's the result of patient, persistent tidal evolution operating over the entire age of the solar system. The truth is, we don't know for certain which explanation is correct. It might have been a giant impact. It might have been tidal evolution. It might have been some combination of both. Perhaps a moderately large impact set Venus on an unusual trajectory, and then tidal forces finished the job over billions of years. What we do know is that Venus's current spin state is stable. Whatever mechanism put it there, it's going to stay there for a very long time. Venus's story highlights something important about planetary spin. The spin state we observe today is not necessarily the result of a single event or a single mechanism. It can be the cumulative result of multiple processes operating over different timescales. An impact might set the initial condition. Tidal forces might then modify it over millions or billions of years. Atmospheric effects might add another layer of complexity. The final spin state is the product of everything that happened to the planet over its entire history. Let me bring this all together now, because we've covered a lot of ground and the full picture is beautifully complex. We started with the protoplanetary disk, a rotating disk of gas and dust that gave every planet its initial angular momentum. This disk biased the planets toward prograde rotation, but didn't determine the details. The details were set by the chaotic process of accretion, where billions of individual collisions each contributed a small random nudge to each planet's growing spin. Then came the giant impacts. In the final violent stages of planet formation, massive collisions reshaped the spin states of the rocky planets. Earth was struck by a Mars-sized body that likely sped up its rotation and created the Moon. Uranus was knocked onto its side by one or more enormous impacts. Venus may have been flipped upside down by a catastrophic collision. Mercury may have lost much of its outer layers in a giant impact that also affected its rotation. Each planet experienced a different collision history, and each one emerged with a different spin as a result. For the gas giants, a different mechanism dominated. Jupiter and Saturn accumulated vast envelopes of gas from the protoplanetary disk. That gas carried angular momentum, delivered coherently from a circumplanetary disk. Then, gravitational contraction amplified the spin through conservation of angular momentum. The result was rapid prograde rotation. Uranus and Neptune followed a similar but less extreme path, ending up with intermediate rotation speeds and, in the case of Uranus, a catastrophically altered axial tilt from a late giant impact. And finally, over the 4.5 billion years since the planets formed, tidal forces have continued to modify their spins. Mercury was braked into a precise 3:2 spin-orbit resonance by the Sun's tidal pull. Venus was driven into slow retrograde rotation by a combination of solar tides and atmospheric thermal tides. Earth's rotation has been gradually slowing for billions of years, with its days growing longer and its angular momentum being transferred to the Moon's orbit. The Moon itself was tidally locked early in its history, and dozens of other moons across the solar system have been locked as well. This is why every planet spins differently. There is no single explanation, no single mechanism, no single event. The spin state of each planet is the unique product of its own history, shaped by the interplay of initial angular momentum from the disk, the random violence of giant impacts, the physics of gas accretion and contraction, the internal structure and composition of the planet, and the slow, patient sculpting of tidal forces operating over billions of years. Change any one of these factors, even slightly, and you get a different spin. Run the solar system again with almost identical starting conditions, and the planets would end up rotating differently the second time. The specific spin states we observe are not inevitable consequences of physical law. They're contingent outcomes of a particular history, a history filled with randomness, violence, and the long, slow working of gravity. Think about what that means. When you look at the planets in our solar system, you're not seeing a neat, orderly arrangement determined by simple rules. You're seeing the aftermath of chaos. You're seeing the scars of ancient collisions written into the tilt of Uranus. You're seeing the patient work of tidal forces recorded in the locked face of Mercury. You're seeing the fingerprint of a forming circumplanetary disk preserved in the rapid spin of Jupiter. Every planet carries the record of its own unique past in the way it rotates. And here's something worth considering. Our solar system is just one planetary system among hundreds of billions in the Milky Way alone. The Kepler Space Telescope and other planet-hunting missions have revealed that planets are common around other stars. Most stars have at least one planet. Many have several. And every one of those planets went through its own formation process, its own accretion history, its own collisions, its own tidal evolution. The diversity of spin states we see in our 8 planets is just a tiny sample of the diversity that must exist across the galaxy. Some exoplanets orbit their stars so closely that they complete an orbit in just a few days. These hot Jupiters, as they're called, are almost certainly tidally locked to their stars, with one face in permanent day and the other in permanent night. Some exoplanets orbit in highly elliptical paths, where tidal forces vary enormously over the course of a single orbit. These planets might be locked in exotic spin-orbit resonances we've never seen in our solar system. Some exoplanets exist in binary star systems, where the tidal forces from 2 stars create complex and perhaps chaotic rotational dynamics that we can barely begin to model. The story of planetary spin is really a story about how the universe creates diversity from simplicity. You start with a cloud of gas and dust, governed by simple, well-understood laws of physics. Conservation of angular momentum, gravitational attraction, the mechanics of collision, tidal interaction. These laws are the same everywhere in the universe. They don't change from one star system to another. And yet, when you apply these simple laws to the messy, chaotic, stochastic process of planet formation, you get an almost infinite variety of outcomes. No 2 planets spin the same way. Not in our solar system, and almost certainly not anywhere else in the galaxy. This is one of the most beautiful insights in all of planetary science. Simplicity at the level of fundamental physics produces complexity at the level of outcomes. The same laws that govern a spinning ice skater also govern the rotation of Jupiter. The same conservation principle that explains why a collapsing cloud spins faster also explains why a tidally locked moon always shows the same face to its planet. The physics is universal. The outcomes are unique. The next time you watch the sunset and the stars come out, remember that the length of your day, the rhythm of sunrise and sunset that structures your entire life, is not some predetermined constant of the universe. It's the result of a specific, contingent, unrepeatable history. It's the result of how a cloud collapsed 4.5 billion years ago. How tiny grains of dust stuck together in a swirling disk. How a Mars-sized body slammed into the young Earth at just the right angle. How the moon has been slowly stealing Earth's rotational energy ever since. Every sunrise you've ever seen is a consequence of chaos and gravity working together across billions of years. And that's true for every planet. Mercury's long, strange days are the product of solar tides carving out a resonance in an elliptical orbit. Venus's backward crawl is the product of atmospheric tides battling against gravitational braking for eons. Jupiter's 10-hour day is the product of gas spiraling inward from a disk and a planet contracting under its own gravity. Uranus rolling on its side is the product of a catastrophic collision that happened before humans, before dinosaurs, before complex life of any kind existed on Earth. Every planet spins differently because every planet lived a different life. They all came from the same place, the same disk, the same cloud. They all follow the same laws. But the details of their individual histories, the specific sequence of events that each one experienced, produced wildly different results. And those results are written into the rotation of every world in our solar system. Permanent records of ancient violence and patient gravitational sculpting, spinning silently in the dark, carrying the memory of everything that ever happened to them. When you understand that, you see the planets differently. They're not just objects in the sky, they're stories, each one rotating at its own pace, tilted at its own angle, facing its own direction, each one carrying the evidence of its own unique journey through 4.5 billion years of cosmic history. And each one reminding us that in a universe governed by simple laws, the outcomes can be endlessly, beautifully complex. Thank you for joining me on this journey through the physics and history of planetary spin. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, every time you watch the sun rise tomorrow morning, you're watching the legacy of everything that ever happened to Earth, written in the steady, ancient rhythm of our planet's spin. Good night, and may you never look at the planets the same way again.